Hello, our last bit of information that we want to look at in section 3.3 is the osculating circle. So in studying the Frenet frame, the TNB, we saw in the part3 how they have this idea of an osculating circle. An osculating circle is like a circle that's tangent to the curve, like a tangent circle, a circle that was best fit that graph. And it turns out that there is a relationship between that tangent circle, the radius of that circle, and the curvature. And that's what we're going to look at now. All right, so the osculating circle is a circle formed on a plane. So if this is in 3 dimensions, then we have to be in an osculating plane. But for simplicity's sake, I think let's just stick with 2-dimensional graphs. And with the 2-dimensional graph, our plane is just going to be the xy plane. So on a point P on the curve, we're going to assume that the circle has the same curvature as the curve itself. So you know how we go from parts of the curve and then you'll have different curvature. Like the curvature for this point right here is going to be, it has a larger curvature because it has more changes than the point over here. So it turns out that the curvature of a circle is going to be given by 1 over r, where r is the radius. So we call r the radius of curvature for that particular curve. And this is equal to the reciprocal of the curvature. So if you're looking for the radius, then the radius is 1 over the curvature. So for the curvature k curvature, I'm sorry, that's kappa, curvature, kappa is going to be 1 over r, or r is going to be 1 over k. They're reciprocals of each other. And by k I mean kappa. All right. So that means if you have a large curvature, like you do in this particular scenario, your 1 over a large number is going to be small, so the radius of that osculating circle will be small. And then if you have a small curvature, then your radius, if you want the same curvature at that point, it'll be like the whole tangent idea, then you're going to have a larger radius for a smaller curvature. Okay, so how does this relate to the TNB frame? So again, we're just sticking with 2 dimensions, so let's not consider the binomial vector right now, but let's just focus on the other two, the tangent and the normal. So we can imagine the tangent going in a particular direction, and then your normal vector would be going in another direction. So the tangent vector for this large circle will be going in a particular direction. Your normal vector will be going that's perpendicular, in a direction that's perpendicular to the tangent vector. So with that, you can see that the center of your circle is going to be going in the same direction towards the normal vector. So we have your unit tangent vector and your unit normal vector, and then once we know the radius of that, which is 1 over the curvature, we can find the radius and go from this point and shoot up to find the center of that circle by just using some vector addition, scalar multiplication to get us to that center of the circle. And so we can create the circle once we have the center and the radius. So the center is going to be the xy point, the radius is going to be your 1 over the curvature. All right, there's an example here we can do. It says find the equation of the osculating circle of the curve defined by this vector valued function. This isn't quite a vector valued function. Let's just say by the function. Excuse me for the typo. Function given by this. So this is an f of x function, and I had copied the formula for the curvature if we have an f of x function. So I think it might be good to figure out what part of the circle this is, or where we are in the circle, or I'm sorry, where we are on this curve. So this curve looks like a parabola. I'm just going to go ahead and, just for the sake of time, I've already plotted this in Desmos, so it's just 2 dimensions, so I can just stick with Desmos. And then I want to figure out where x is equal to 1 is going to lead us, and x is equal to 1 is actually this point, 1 comma 3. So this is great for us because it's an actual vertex of a parabola. It's the minimum, and it looks like your tangent vector is going to be, your unit tangent vector is going to be horizontal. Then that would make your normal vector to be vertical. All right, so let's take note of that, and let's copy this and then annotate over it. Now this is not a vector valued function. It is a y equals f of x function, but let me show you how we can make this into a vector valued function to consider the tangent and the normal vectors. This function over here can actually be written as r of t. I think we've done this once or twice before. I can just take my t variable and make that my x, because x seems to be the independent variable in this scenario. So t is independent, and then my y is dependent on x, which is now equal to t. So I will have my y value to be 2t squared minus 4t plus 5. And so when I do things like find a derivative, r prime of t, this is going to give me 1, and then whatever the derivative here is, that's 4t minus 4. And then when I put 1 in there, r prime of 1, this is going to give me 1 comma, and this is 1 minus 1, 0. And this happens to be a unit vector already, and so that's great news for us, because that's just going to be your t evaluated at 1. Now your unit tangent vectors at other points might not be so easily computed. In fact, it's probably going to be a lot more complicated, but we're not going to go there. We don't need to. Now we will also be interested in finding the derivative of the derivative to find r double prime, because r double prime is the acceleration, and the acceleration will help us figure out which way the normal is going. So right now we have our normal vector going in this direction, so each of these things are 2, so this is just one unit right here. This is your capital T, your unit tangent, and you have 2 choices for your normal. Your normal will be going up or it can be going down, so it depends on which way it's going, and it depends on your acceleration. So if we take a look at your acceleration, we get 0 and 4. So your acceleration goes in the y direction, does not move into x, and that makes sense, it's perpendicular. But now we want it to be the binormal vector, I'm sorry, the normal vector, and so we're just going to make that into a unit vector. And I don't think we need to do any work for that, because it's just going to be 0, 1. So this is your normal vector, n, and what I drew here would have been your acceleration vector. So let's take that out. Maybe we'll draw it lightly. This is your a of t, or your r double prime. Okay, so we have our unit tangent and unit normal vectors. Now let's find our curvature. So to find our curvature, we need the derivative and second derivative of this. So let's go back to our y function. y is equal to 2x squared minus 4x plus 5, and then let's find the first and second derivatives, y prime. We already did that, but let's go through it again. 4x minus 4, y double prime equals 4. So that's just a constant up on top. It's positive already, so we can just ignore the sign or the absolute value. And then in the bottom we have 1 plus, and then we have 4x minus 4 squared, and then take that to the 3/2 power. We're going to put 1 in here. So x is equal to 1. Let's put x is equal to 1 there. And if x is equal to 1, this thing just becomes 0, I believe, right? So it'll be 1 plus, and then inside here is 4 minus 4, which is 0. So this is just going to be, so your curvature is going to be 4. All right. So now that we know the curvature to be 4, we can expect our radius for our osculating circle to be 1/4. So r is equal to 1/4. Now, what we're going to do is we're going to go from this point here, 1, 3, and we're going to go 1/4 step in the unit normal direction. So what we can do is the center of the circle will be the point 1, 3 plus 1/4 times the unit vector, a unit normal vector 0, 1. Okay, and so you probably could have seen the geometry here and just say, oh, I'm going to go 1/4 up, so this is going to be 3 1/4 going up, but this is, you know, officially you want to get to that point, and then you want to add that normal vector to it, scaled to whatever the radius is. So this is going to be 1 comma, and this is let's see, do we need to add 12, 13? So this is 13/4, or 3 and 3.25 if you want. So this is going to be the new center of the circle. So our circle will have this center. So the center is going to be 1, x minus 1 squared plus, and then the y and a new center 13/4 squared is equal to the radius r squared. So that should be your circle. Let's go ahead and check if that's true, and let's hope that it is. So if I type in the circle x minus 1 squared, and then plus, and then we have a y minus, I think it's 13/4. We'll close that up and square it, and then say that that's going to be equal to 1/2 quantity squared, and oops, this is 1/4, sorry. And there we go. So if we zoom in and take a look at that, it looks like it's mimicking this circle exactly at that point. All right, so it's really dependent on how it's moving along the x and x axis. So I do want to, so let's put that point here, and I believe that point was 1 comma 13/4. So we can see that center of that circle. Okay. All right. If you want to make this generic and you do a bunch of computations, it turns out that Desmos can do that for you. And so I wrote a little program that allows you to move around and see what happens to the circle as you go along. And as you go to parts of your curve that are flatter and flatter, your curvature will get closer and closer to 0, and then the reciprocal of that will get really, really large. So I'll need to zoom out to find the center of that circle, and if I keep going further out along that curve, your circle will just get bigger and bigger. And so there's a lot of interesting aspects to being able to view this. And if you do it correctly, you can do all these computations. You can just, for me, I can just change this into a different curve. And then there's also some nuances in the particular discussion, or when we're talking about that curve, and that the curvature is always positive, but your normal vector may be pointing in opposite directions. And so when that happens, it has to switch back to the other side of the normal vector. And those moves are not necessarily smooth or continuous, but here we can take a look at, for example, the sine function. If we go along the sine function, the smallest curvatures, or the largest curvature and the smallest circles, happen at the maximums and minimums. And then at these inflection points, you know, those inflection points are where it changes concavity. So you get from going down, and then at some point your normal vector switches sides, and then at that point where they switch sides, you have a curvature that actually will equal to 0, and your radius of your osculating circle now will become infinite, and so it switches off and makes a circle on the other side of the graph. And so you can see that happening here. Okay, so I suggest you try to mess around with the graph, or the graphing program, and see if you can create something similar to this, because it's kind of fun, kind of cool. Okay, so that's it for section 3.3. So we've covered a lot of stuff, and now we can find out a lot more information about the curves in 2- and 3-dimensional space. All right, hope that helps. Have fun.